Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Jeff Tate, the CEO of FlexLogic, who's going to talk today about edge inferencing and the streaming and pooling of data. Jeff, there's a lot of terms out there for what's going on the edge. What's the difference between streaming and pooling?
There's a lot of terms that people have heard: edge processing versus data center, latency versus throughput. And what we're finding as we talk with customers is that the issue, perhaps is more importantly, are they processing a stream of information or are they processing a pool of information? So in the data center, typically, you may be processing pools of information. If you're Google and there's photos and you're going through and tagging all the photos, that can be done at any time, day or night. And what really matters there isn't latency. It doesn't matter if it takes a second, a minute, or an hour. What matters is getting through as many photos as possible to use your hardware efficiently. So that's processing a pool.
Is there a difference in power consumption between the two of these?
Well, my point is you don't have a choice. If we're taking the first example where it's a photo album and you're processing, it's a pool of data. And your objective is always to do the most work with the least resources. So you would then do large batch sizes and so forth to do it efficiently. But if you're in most typical edge applications, what you're processing is not a pool of data, you're processing a stream of data. You've got a camera mounted somewhere and 30 frames per second images are coming in and you have to process them and you have to keep up with them. If you don't, then serious consequences can happen, like hitting somebody.
Let's drill down into this.
So when we deal with our customers, most typically they have a camera and that camera is producing 30 frames per second. And each frame is about typically 2 megapixels, although sometimes people have larger or smaller images. 30 frames per second, it works out to about 33 milliseconds per image. And if you have an image coming in this stream, how you process it depends on what you're trying to do. Let's take 3 examples. Let's take an example of where you're in a store. And in the store, you're counting how many people are in line at any given time. So you're generating retail analytic information. In another example, you're in a store and you're looking for somebody who is doing shoplifting. And in the last example, you're driving in a car and you're trying to make sure that you don't hit pedestrians. Now you can see why I'm a CEO and not a graphics artist. In one example, in all these examples, the camera is generating images 1 frame per second, 33 milliseconds. In something like this case, where you're counting people staying in a store, there's several issues. One is you may not need to produce the information for hours. If the store management gets a report every day saying what average line lengths were and so forth, maybe that's all they need. If you're trying to catch a shoplifter, if you find that you've found somebody, maybe you have a minute before they leave the store, so you have to alert security to intercept them. If you're in a car, you have milliseconds, because if somebody's walking across your path, you need to slam on the brakes. So just because you're dealing with a stream doesn't mean that you'll deal with it the same way. And as you process the stream, you have 3 things that you do. One is you clean up the image processing. So when the sensor produces images, you may have, especially in a car, you may have streaks of light and contrast issues you need to resolve. So once you have an acceptably clean image, then you do the inference. And when the inference is done, say it's detecting objects and recognizing them, then you have to take action. And depending on the activity you're dealing with, all of this needs to happen in a certain period of time, much less in the car and perhaps more in other situations. And these are just a few examples. Every example is different in terms of how critical it is. But if you're dealing with examples like this, which is what we'll focus on for now, what matters is minimizing the latency of the inference. You also have to minimize the latency of the image processing and of the decision processing, but we're talking here today about inference.
Jeff, what does that do in terms of the design? What do you have to think about when you're designing this now that is completely different from what you would do in each one of these? How does it change?
If you're looking over here, you have to pick elements which will get you the image cleaned up, the inference processed, and the action taken in a short enough period of time to meet your objectives on safety. Of course, you also have criteria of power and cost. If you're dealing with a situation like this, your trade-offs are much different. You over here could actually treat the data, even though it is a stream, you could treat it as a pool. If you really don't need the results for hours, you could do batch processing of the images if that got you better throughput, because latency doesn't really matter in that case. What matters is getting the most images processed with the least cost and power. So that would cause you to pick different inference accelerators in the different cases.
So from a design standpoint, what does that actually entail? Is it a different throughput to memory? Is it more different kinds of layouts in terms of the processing elements that are on the chip? How does that change?
So the applications that we're dealing with customers are characteristic of more like a car. We're talking with people who have a wide range of applications: biomedical, medical imaging, retail analytics, aerospace, where people want to detect bad objects coming their way. So our customers are looking for processing a stream in a relatively short period of time within power constraints. And our customers typically want something like 15 watts max power. They're looking for, something that costs double-digit dollars, and they're looking to get as many frames per second of processing as they can with the lowest latency that they can. That's the characteristics of the customers that we're dealing with. So I want to point out latency and streaming throughput as the next step. If you have an image and you have two alternatives, say one alternative meets these criteria and they say that they can process 30 frames per second. And typically what people are doing is talking about throughput. And another application says that they can process 15 frames per second. Which one is better? What people will initially think is that this one is better. Well, what if that one is getting its throughput because it has 3 engines inside it, and each of those engines has latencies of different length? And I'm referring to specifically here Xavier NX or AGX. The DLL, the deep learning engine in Xavier, takes something like 300 milliseconds to process an image. The GPU inside Xavier, and there's 2 of these, the GPU takes about 90 milliseconds to process an image. So if you have 2 of these running and 1 of these running, you can get some significant throughput. The issue is if you're processing 1 image at a time, you can't really effectively use this one. And now the throughput of this goes down to more like 10 frames per second, 90 divided into 1,000 milliseconds.
And you've also ratcheted up the power that's needed in order to do this, right?
Yeah, and there's a lot of details that we don't have time to get into here. So you have to look at the power characteristics. If you're using less of the thing with the NX is it's a power throttled chip. So if you turn off the DLLs, you're not necessarily changing anything because it's got a 15 watt maximum. And the chip really, if left to its own devices, probably would run up at 35 or 40 watts.
So looking at that number, what's the actual impact in terms of your 30 frames per second versus 10 frames per second?
Okay, so the 30 frames per second, this is what you can call, let's call it pool throughput. If you had a pool of data and you have 3 execution units like in the NX, and what you want to do is process the pool as quickly as you can, then and maybe it does do 30 frames per second. But if you have a stream of data, you're looking at the latency of the fastest execution unit, and that divided into 1,000 milliseconds gives you your frame rate, a little over 10 frames per second. So this is streaming throughput. So streaming throughput is where you are processing at batch equals 1. And pool is where you're processing at batch equals many, or using multiple parallel units. So our customers care about streaming throughput because they're processing a stream of data, and they can't utilize execution units that run more slowly, even if they're quotes free.
And so if you think about a car, this is pretty much a camera that's watching what's going on and you're being able to process it as it comes in, right?
Yes, yes. And in the applications our customers have, what they need is they need the image that is being processed, the processing to be complete before the next image is available. So you have to keep up. If you don't keep up, then you'd have to store more and more data, and your latency would be longer and longer. And of course, then you'd have fatal consequences if it was a car. Your alternative is to go to slower frame rates, but that can have disadvantages too if objects are moving rapidly.
So this all makes sense on paper. The problem is that you also have almost constantly shifting algorithms here. So you think about a lot of these markets; they're really nascent. They're just beginning to get going. The algorithms are changing almost by the day. How do you future-proof something like this?
When you're designing a inference accelerator, and the ones that are coming out this year were designed starting a couple of years ago, you have to have something in mind. What are you optimizing for? And what I predict is that most inference accelerators that are coming out will have been optimized for ResNet 50, which we've talked about before as a bad benchmark, not because of ResNet 50, but because it's associated with small images, 224 by 224. What we focused on was YOLO V3, and we focused on 2 megapixel images, which are 1440 by 1440 squared. And this requires a much more robust memory system. So we have been talking with customers in the last 6 months who've approached us because existing solutions do not meet their needs. They are using solutions like, say, a Tesla T4 or an NVIDIA Xavier. And I'm not picking on NVIDIA here. The fact of the matter is NVIDIA has done a great job and dominates this market. So that's what everybody is using. But the customers that come to talk to us say, I really need more frames per second, or I need more resolution than what I can get out of this solution. Can you give me more inference capability within the same cost and the same power envelope? And we have seen models that are tremendously different from both of these models. In spaces like biomedical engineering or medical imaging, they're processing different kinds of sensors, and they are not like doing, pedestrian object detection and recognition. They're using neural networks in a very different way. And the advantage that we believe we have, because what we find is that compared to Xavier, we're very good on YOLO V3 compared to Xavier, but when it comes to these other models, we're even better. And that's because in our architecture, we have compute resources like 64 max in the cluster, but our clusters are wired together using our XFlex interconnect. So we can rewire our clusters in programmable ways to implement operators and convolutions like a 3D convolution that were not anticipated when we first set up the architecture.
Jeff Tate, thanks for a great explanation.
Thanks. Great to be with you.